studied about the ternary alloys and quaternary alloys, and then we have studied about the light emitting diode and its characteristics, as well as we have studied about homojunction, heterojunction, and we have studied about the double heterojunction LED, which is important with respect to your exam. Okay, so next we go for the configurations of LED. There are two configurations. There are two types actually. So one is the surface emitting LED. Another one is edge emitting LED. So there are two ways in which the light is generated that we will go through in this class. So both devices uses double heterogeneous structure. So we have seen what is an heterojunction, and then we have seen what is single heterojunction and double heterojunction. So it uses the double heterojunction structure, which we have discussed in the previous class. Okay, so we'll go one by one. First is the surface emitting LED. So there is a vertical section which has been taken here, vertical section of the SLED, surface LED. Okay, so double heterojunction structure means there should be a two heterojunctions here. So again, if you observe, so this is aluminum, gallium arsenide, and gallium arsenide. So the junction between the two different semiconductors, which are of two different band gaps, is given here. This is one heterojunction. And from this side, there is an N-type aluminum gallium arsenide and an N-type gallium arsenide. So this junction is again an heterojunction because these are the two different semiconductor materials which are of different band gap energy. So this is an homojunction because it is an N-type ALGAS. It's okay. Yeah. So there are two double heterojunction structures are there, and this is your active region. So the center region is called as an active region. So this you consider it as N-type or P-type ALGAS. Okay. So and then on the left side you have SiO2, both the sides SiO2. This will act as a blocking layer. I'll explain that. And this is for metallization. Again, on the top side also, on the top you have a metallization process. From this you can connect the positive terminal or a negative terminal. So from this side you can connect positive or negative terminal. Okay. So this is an etched well where the generated light is transmitted, and this is your optical fiber. So we have etched that particular LED, and we have placed an optical fiber so that the light passes through this optical fiber for propagation. Okay, so if there is any light which is deviating after it is generated, so that will be taken care by this epoxy resin, so uh, which stops the light to radiate outside, and it confines the light again into the optical fiber. For that purpose we have a epoxy resin. Okay, now we'll go one by one. So N-type, you have an N-type gallium arsenide, N-type ALGAS, and P-type ALGAS, and P-type gas and blocking layer. So this works in forward bias condition. We know that. So you have N-type, so connect it to negative terminal. So you have a P-type, can connect it to positive terminal. So the input to your LED is the current pulse. Okay, that you should remember. So but this so whenever the positive terminal is connected, all the holes which are present here will be pushed to the next layer. And this the P-type ALGAS consists of the holes again it will be pushed to the active region. So similarly, when you are connecting the N-type GAS to the negative terminal, electrons present here will be pushed to here. So next it will be pushed to here. Okay, that means all your electrons and holes come to the active layer, that is your N-type or a P-type ALGAS. So this layer, all your electrons will come as well as holes will come. And so we have wherever we have to generate the light. This is surface, so it's a surface emitting LED. So we want only the light to be transmitted in this region because my OFC is here. If any light which is generated here, which will waste it. Okay, so that's why this is where the recombination happens. The holes which are coming into this layer and the electrons which are coming into this layer will recombine, and this recombination will generate a light. That is through emission, okay, spontaneous emission, which we have seen in the earlier classes. But our main intention is to push your electrons and holes in this direction. Why? Because my OFC is here, because if any recombination happens here, then there are chances that the light may go in this direction or in this direction or in this direction. So I want my light to be confined to this. So that is the surface emitting LED. So that's why we have metallization here, and that's why we have the blocking layer here. So whenever the holes which are here, if they come back, if they are coming here, they will be pushed. So there is no there is nothing which will come out here. They will be pushed in this direction. If there is no blocking layer, there are chances that this may combine with this. So as it's a blocking layer, it will push your holes to in this direction. And also at this point, if you have a blocking layer of metallization, it will push your electrons in this direction. Okay, so your holes and electrons will be pushed in this direction because due to this blocking layer. Okay, here you don't have a blocking layer. Okay, so the the holes will move in this direction. The holes will also move in this direction. Electrons are moved in this direction. Initially they will not move. Later, once they are pushed from this metallization, they'll come in this direction. Okay, the electrons will come in this direction, holes will come in this direction, and they will recombine in a small area. Okay, once they recombine, they generate an energy in terms of your optical wavelength. Okay, that is in terms of photons, and these photons are of a particular bandwidth, and they are generated. So different colors have different bandwidth. So based on the bandwidth, so based on the lambda required, of lambda of interest, so you can use different materials that we have seen in the earlier classes, and the light is generated. Okay, so once the light is generated, so it is not that all the light is generated in this direction. So some of the holes will be here, holes and electrons will recombine here also. So most of the part will combine here, but there are cases that the electrons and hole will combine here also, here also. So once they are combined, there are chances that the light may go in this direction, light may go in this direction, this direction. So light will travel in all the directions. But as we are moving the electrons and holes in the active region, there are chances that most part of the light is generated in this direction, and it will be captured by your optical fiber. So if anything is going in this direction, again it will be pushed by an epoxy resin, so that it can transmit through your optical fiber. Okay, that's why we have an epoxy resin. But there are chances that the light may go in this direction. Some amount of the light will travel here, which may be wasted, or it may again recombine and generate a light. So that is your surface emitting LED. Okay, so we have taken an LED and we have taken the vertical section of it. This is the vertical section of your LED. The same double heterojunction structure is used. Whatever we have discussed in the earlier classes, the same double heterojunction is here, and there are advantages why we actually use the double heterogeneous structure. I hope you have understood. So for that, after explaining this, you have to write the band gap energy. So what we have written in the last class. So the band gap energy for this, for a different layer. So the energy the present in these different layers are represented using an energy diagram. So this is the center layer, that is your active region. So this is your active region. So in active region, the band gap will be less. Okay, the band gap energy, what we have discussed in the earlier classes, will be less. The double heterojunction, so this is one single heterojunction, this is one single heterojunction. So at these two layers, so the energy band gap will be more. Okay, they are two different. This energy band gap energy will be more here, band gap energy will be more. In active layer, the band gap energy will be less. Okay, so once the band gap is less, it gives a chance for your electrons and holes to recombine very quickly, as it has to jump to a lesser with a lesser energy, and they generate photons. Okay, so the generated photons will come in this direction. It may go in this direction also. So most of the cases it will generate here. But as the light comes out from the active region, So it will not go again into the other layers and recombine, because the band gap between these two is more. So there are less chances that the photon generated here will come out very easily, instead of again going back and recombining with the electrons or the holes which are present here, which are present there. Okay, so the band gap is very less, which generates an energy in terms of light in this direction, and it also generates in this direction, it also generates in this direction. But if it was less, if in the case if you have used an homojunction, then there are chances that the light will again recombine. That's why we have used an heterojunction structure at both the sides, so that the light will not recombine. If the light recombine, again there are chances of amplification. So that will be used in case of your spontaneous emission, not in case of so that will be used in case of stimulated emission, not in case of spontaneous emission. So chances of reabsorption is less. If the light is generated in this direction only, then there is a chances of recombination again by going here and combining with the electrons or holes present there. Okay, so the main thing is it avoids reabsorption losses. Reabsorptions will be less. Okay, that is the first thing. So next is carrier confinement. Carrier confinement means we have made all the electrons and holes to come to this particular region. So the carrier is confined here, so that you can generate a light in the one direction. So our carrier is confined in one. This is another important property thing. So for the same given current, the excess carrier configuration becomes very large in small dimension, that is the delta n will be less. Okay, so this is your band gap energy, so energy diagram. So next, there is another three properties. One, it avoids reabsorption losses, carrier is confined, and then once the carrier is confined, recombination happens and the light is generated, and the optical confinement is also there. Okay, so the light is generated and it is confined to this, that is optical confinement. Here the light may generate in other directions also. That's why the optical confinement is somewhat less in case of your surface emitting led, but in case of edge emitting led, which we are going to discuss next, is optically confined. So three properties you can write here, but optical confinement is somewhat less compared to edge emitting led. Optical is the light is confined to the one region. Okay, so yeah, once you have written the energy band diagram, so you can also write the refractive index. So we know that the refractive index is inversely proportional to the band gap. So that is in nature. So if the band gap is less, that is in active region it is less, in active region refractive index is more. So other sites where the band gap is more, in your heterojunction, refractive index is less. So that is the relation between the band gap and your refractive indices. Okay, so always write this diagram along with your energy band diagram also. Refractive index with respect to x, and this is energy with respect to this. Okay, so that is what I have written. Smaller band gap energy as a large refractive index, larger band gap as a lower refractive index. And so the generation of your light is explained with respect to this refractive index. I will take the refractive index and explain the same. So I have just written this. So this we will consider this as the refractive index as n1 at this point, n1 at the active layer. Other sides I will take it as n2, which is lesser compared to n1. At the active layer n1, other layers n2, which are less. So if you want to explain that with us, N1, this is your active region. These are the other two regions, heterojunction regions. So, and N1 is always greater, so N2 is less. Okay, so once the recombination happens here in the active region, the light is generated. Some of the light is confined here itself, or some of the light will go. So we know the basics of optical communication, that so if the light is generated above the critical angle, the light will come propagate within this particular layer itself. Or if it is generated lesser than the critical angle, then the light will go out to the next layers. So here we are not, if the light is confined within the region, the light will propagate here itself and comes out if there is an opening or an edge. If there is no opening, it will be propagating here itself. That is what we don't require in this case. We require it is a surface emitting, and we have made an opening here. So if you see the diagram, we have made an opening here. The light has to come out here, not here. So if it comes out here, it is called as edge emitting LED on the edges. Other, if it is a surface, it's a surface emitting LED, it has to come out. Okay, so some of the light will come out, some of will propagate here itself based on your N1 and N2. On the other sides N1. So the light which are coming out here will be taken through your H well through to OFC cable. Okay, that is your surface emitting LED. So yeah, so whatever I explained with respect to your refractive index, it is here. So at the sides, if it open at the sides, it is called as edge emitting LED. That is the concept of edge emitting LED, which will see through. So SLEDs, the surface LEDs, yeah, the bit rates are 250 megabits per second, and they emit a light on the wide area. So they emit light at a wide area, that is at a different wavelengths, and they are exclusively used for multi-mode systems. And so whatever you see in case of your display, so wherever the display is there, so there your SLED is used because it is generating at the surfaces, okay, and at a wide range. So if it is at the edges, we will not use it. If it is at the edges, if the light is generated at the edges, it is very directional, only in one direction. People who are sitting in this direction can see if you use edge emitting LEDs in display. So it has to take the light from different directions, so that when people are sitting in front of the TV and all these things, the wide angle should be there. So otherwise, if you are edge emitting LED, if you have used for your TV and all these things, what happens? Only the people who are sitting in this direction will see. So people who are sitting in this direction will not see. So that's why it is used for comparatively shorter distances compared to edge emitting LEDs, and it generates a wide band. So it has, because then that's why it is used for your display purposes, SLED. Okay, so a well is etched, whatever I explained here, the well is etched into substrate or the direct, so it couples the light to the optical fiber. Etched well is used for emitting surfaces, and there is an epoxy resin which confines the light in that particular direction. The light is generated will be like this. In terms of beam angle, it is look like this. Okay, next is edge emitting LED. Same explanation, same thing, same explanation, but here the optical confinement is more. So whatever I explained, you explain here itself, except the specific characteristics of SLED. Leave that, and it avoids reabsorption losses. It avoids, and so it leads to carrier confinement. It avoids the optical. So it gives the optical confinement. More confinement will be here. So that is a very important extra property of edge emitting LED. The optical energy which is generated in active region is confined because of the optical wave guiding action. So it is suitable for digital systems up to 140. It is normally used for your optical fiber communication because the light is generated very linearly. Okay, there will be a linear relationship, and it is highly directional beam is generated. Highly direction beams are not used for display. Here, if instead of taking the HL here, we have taken the opening at the edges. Okay, and the light which is generated at the edges are taken out, and the cone, the beam cone, it look like this. So within this cone, your light is generated. Same explanation, same double heterogeneous structure, same energy band diagram you have to write. Instead of taking at the surfaces, we are taking at the edges, but here the light which is generated is very directional beam. Okay, not parallel, but it is a very directional beam which is generated at the edges. That is why optical confinement will be there. So when it is very confined, optically confined, then it is best suited for your optical communication, but not suited for your display purposes. Okay, so there is a linear relationship between the optical output and the current, and you have a better coupling efficiency. You can couple very easily, as it doesn't generate the light in various directions. So as it is directional beam, you can coupling efficiency is more, and it is also temperature sensitive, and usage is, can be used for a long distance compared to SLED. It is used for a long distance communication. Okay, so it uses a double heterogeneous structure. So if you want to write energy diagrams, write the same energy band diagram and also the refractive index. Same explanation, except you are taking at the edges of the light. That is your edge emitting LED, and the cone will look like this when you take at the edges. Okay, it avoids reabsorption loss also. Same explanation. Okay, so these are the two important LEDs. If they ask only double heterogeneous structure, explain the first, which I have explained in the earlier classes. If they specifically ask for surface emitting LED and edge emitting LED, or they ask for it for LED configuration, then you can write on this one. Okay. Okay, so practically you have seen a LED, which is a display LED, which you have used in your labs, in your LD. So is whatever I explained, the LED, it is in terms of a chip and it is placed on an electrode. So this is not there for your syllabus, just for your understanding I have written out. On an electrode, your LED chip is placed, and this is negative terminal, positive terminal, this is an electrode, and this is your epoxy resin, okay, or an acrylic plastic. So that your red LED, which you use white LED, so whatever the light is generated, it again confines here itself. So it acts as a dielectric within that, and this is your negative electrode, positive electrode, and the light. It's a small chip. Whatever explanation I have done, it is placed in this particular part. Okay, so it acts as a dielectric capacitor. This is not there for your syllabus, just for your understanding. Okay, so light source materials we have already studied in the earlier classes. So light source material, it is semiconductor are made, so it is there for your syllabus. If they ask it, you write it. So what is spontaneous emission, what is stimulated emission, that you go through it. And we explain about the direct band gap, we explain about indirect band gap, which I have explained in the earlier classes. And so I've already noted down the energy band diagram, and recombination rate is the extra thing. So direct band gap, indirect band gap. So what is the band gap energy, you note down that. So whatever explained in the earlier classes, you can also put in this light source material. Okay, so then we have taken, so this is the light beam which is generated, this is the various this is the band, this is the band is called as full width of maximum spectral width. This is the light which is generated. If we take with respect to the output power and wavelength, it look like this. And this you can change with respect to taking the material. One gallium aluminum arsenide with X is equal to 0.08, that is a mole fraction. He has taken one example and written it down. And then we have studied these things. We have studied E is equal to h nu. H nu is frequency. Frequency is equal to C by lambda. Lambda is equal to hc by E. So this is Planck's constant C. C we know. So if you do that, you get 1 point. If you combine, multiply that, 1.24 divided by Eg electron volts. So lambda of interest is generated based on the band gap energy of the material. Same explanation, whatever explained in the earlier classes, you can use it here in case of light source materials. Okay, and we have seen this also for a ternary alloys. Eg is calculated using for a quaternary alloy. Eg is calculated, the band gap is energy is calculated using this expression. Quaternary, 4 different types of semiconductor material. Quaternary alloy, ternary alloy is 3 different types of materials. Okay, so whatever I explained in earlier classes, you can put down if they ask it in terms of light source material. Specifically, if they ask source and edge emitting LED, you explain this. Normally they ask double heterogeneous structure and write the energy band diagram and its relation with refractive index. Okay, so I hope you have understood to some extent, and I'll stop my share. If you have any questions, you can ask, or just be there for 1 or 2 minutes. I'll take your attendance and then we'll stop. Okay, okay, just be there for 1 or 2 minutes.